right, you have a new homework assignment, and this will be the last one. Hooray. So let me introduce it to you. And I'm also thinking for the second exam, what I'm going to do is a take-home exam. So I'll give you some data and a PDF with tasks on it, and you'll have, let's say, 2 days to do it. That's intended to give you more time with writing your code and that kind of thing. So a big gift or a big favor you can do me is not collaborate with other people on that, please. The main reason we like to have them in the classroom is so I can watch the people here, and then I arrange for proctors for everybody who's not here, everybody who's at a distance, and then they have a person watching them. But that has the limitation of you only have X amount of minutes to do it. So we'll try it and see how it goes. No final exam. I just essentially have 2 midterm exams. Let's see. So this homework assignment is survival stuff. And there's 3 problems. The first problem is all about survival curve estimates. So I have some data, serve times data. Let me make sure they're up here. Yeah, I think this is it right here, serve times. They're actually organized in a CSV file. The homework says .text, but it is a CSV file, so you can just use read.csv. Okay, so what we have is 2 comparison groups, and for each comparison group we have survival times. Y1 is for group 1, those are the survival times in group 1, and delta 1 are the censoring indicators for that group. So every 1 is an actual death, and every 0 is a right censored observation. Then Y2 and delta 2 are for the second comparison group. You can just ignore this first column. That was just row names that got added to the file when I wrote it to a file. So all we care about is Y1, Y2, delta 1, delta 2. Okay, so I want you to make separate Kaplan-Meier survival curve estimates and plot them for the 2 comparison groups. Comment on who looks like they're in a better shape. Of these 2 groups, who has the better survival prognosis overall? You would answer that by looking at whose survival curve is higher or tends to be higher across the range of event times. Then in part B, I ask you to compute what I call the empirical survival curves, and all I mean by that is ignoring the censoring information. So essentially treating every single one of these times as an actual death. That means that at every single one of these unique times, there will be a drop in the survival function. Whereas Kaplan-Meier keeps things at the same place for censored individuals. So think about how to do that. It's not a hard calculation. You just need to compute proportion of deaths compared to number at risk at each unique event time. what proportion of those at risk at each unique event time survived. That's your estimated empirical survival curve estimate. So compute that and compare it to the Kaplan-Meier curves so you can see what the difference is. Then in part C, I ask you to compute the mean survival time for each group based on the Kaplan-Meier curves. I'll show you how to do that today. And I ask you to compute some percentiles of the survival times based on the Kaplan-Meier curves, and I'll show you how to do that today. I ask you to test the null hypothesis that the survival curves are the same between the two comparison groups. And to do that, we're going to use a test called the log rank test that I'll introduce you to today. And then I want you to do maximum likelihood estimation of the survival curves. Kaplan-Meier is a non-parametric survival curve estimate. There's no assumption of a distribution of the survival times. And as a result, we get kind of a rough estimate, a step function estimate. But if we assume that the survival times themselves have a distribution, and you're going to assume they're normally distributed, then we can specify a likelihood and use that to estimate a smooth survival curve. And the MLE survival curve will look a lot like the Kaplan-Meier curve, except it won't be a step function, but it'll go right through the middle of it. I'll remind you how to do likelihood stuff either today or Monday. In the notes for the survival data, we have a few slides that show how to put together a likelihood. And if we have time, I'll review that today, if not Monday. I'm asking you to use a function called Optum, which is a generic optimizer, numerical optimization function in R. So if you give a function to Optum, it can algorithmically find maximums. So we're going to give Optum a function that implements the likelihood and let it numerically maximize the likelihood, find the MLEs for us. And then I ask you to use a Bootstrap analysis to get a 95% confidence interval for the difference in the population mean survival times, using maximum likelihood as the estimation routine. To bootstrap with survival data, we sample, what you would do with these data is sample with replacement from group 1. That would mean sample from the rows 1 through 183. Sample 183 of the group 1 individuals with replacement. And when you sample, you need to keep the survival time and the censoring indicator together. So if the first individual that was sampled to be put in a bootstrap sample was number 3, I would go get this individual's 12.42231 and their delta equal 1. So similar to what we did with correlated data, when we bootstrap, we need to keep those two things together. And with correlated data, we had to keep all the repeat measurements on the same individual together. With survival data, we have to keep the Y together with its delta. So what I would ask you to do is separately sample with replacement from group 1 and group 2. You don't need to sample keeping all the numbers together on the first row, because Y1 and Y2 are not paired in any way. They're not connected to each other. So you would separately sample with replacement from group 1 and separately sample with replacement from group 2. You might get different individuals, different row numbers in the two groups. The next two problems are similar, to themselves. They're different from the previous one, but they are similar tasks to themselves. We're going to see an example script next week called WAS 500. These are survival data, and we're going to do regression with survival data with these two data sets. Previous problem was not regression. That's just fit survival curves. Now, next week, we're going to learn how to do regression with censored data. The type of regression that I'm going to emphasize is a model called the Cox proportional hazards model. It's a widely used technique for doing regression with censored data. So we'll talk all about it next week. But in this script, I pulled out some material from the proposed textbook in the syllabus, the Regression Methods in Biostatistics book. They had a nice chapter on model building. We've talked a little bit about model building. How do you choose whether to treat a covariate as a linear function or quadratic, for example? How do you choose which covariates to put in the model and which covariates to not include in the model? How do you assess whether the model assumptions are reasonable? We've talked about that some already a little bit. But they have a nice 5-step model building process that I'll talk through next week, and I'm asking you to do the same thing here. So you're going to look at 2 data sets, these lung data that come with the survival package. So that means if you go to R and library survival, you can get, for example, the lung data. Now that survival has been libraried in, we can get the lung data by just saying data lung. Now if I say question mark lung, we get some documentation about it. The lung data are survival times in patients with advanced lung cancer from a particular cancer center. And we have performance scores. Part of our covariates are performance scores that rate how well the patient can perform usual daily activities. Time is event time. Status is censoring, and they have it coded a little bit differently. They have it coded 1 for censored, 2 for dead. We've been saying 0 for censored, 1 for dead. I'll have to double check on whether we need to change that, recode it. I'll speak to that next week. We also have age, we have gender, and then here are performance scores. So 3 covariates that measure ability to complete daily tasks. Calories consumed, how much are they eating, and how much weight have they lost in the last 6 months. So you'll build a regression model that says survival time or a function of survival time. What we actually will do regression on is what's called the hazard function that I'll define soon. So we model the hazard in terms of these covariates. Let's briefly look at the other data. These are also included with the survival package. So let's do data ovarian and question ovarian. Randomized trial comparing 2 treatments for ovarian cancer. Foo time, like follow-up time, is the survival time. Foo stat is the censoring indicator. We have age. We have an indicator of whether some residual disease is present, yes or no. We have treatment group and some kind of performance status. I think this is similar to what we had on the previous data set. Okay. I want you to interpret one of the coefficients of the model. Working with Cox proportional hazards regression models, you have to use special language when interpreting the coefficients. When we do linear regression, we interpret a coefficient as a mean change in the response associated with a 1 unit increase in the covariate, holding everything else constant. With a proportional hazards model, we interpret let me back up and say, with another type of regression, logistic regression, which is the type of regression we do when we have 0-1 data as the response, success, fail, death, dead or alive, that kind of thing. We interpret coefficients as log odds ratios associated with a 1 unit increase in the covariate, holding everything else constant. With Cox proportional hazards, we're going to interpret the coefficients as log hazard ratios associated with a 1 unit increase in the covariate, everything else held constant. So I want you to have a little practice in interpreting one of those. And then I ask for a confidence interval for a hazard ratio. The coefficients are log hazard ratios. So you're going to have to compute a confidence interval for a coefficient, and then what you can do to turn it into a confidence interval for a hazard ratio rather than a log hazard ratio is just exponentiate it. Again, I'll give you examples of all of these when we look at some example data next week. Okay, so for now, let's go back to the serve script file. There's a couple of other things I wanted to show in here before moving on in the notes. Okay, so let's come down to line 23, where I'm going to simulate some right-censored data from a normal distribution. Let's say that survival time is normally distributed with mean 5, standard deviation 1.5, and let's say that 30% of the individuals are going to be censored. Let's make it a bigger sample size. How about 100? So n is 100, mu is 5, sigma is 1.5, the proportion uncensored is 0.7, and here are the survival times. These are uncensored survival times currently. I have not imposed any censoring. Survival times. Actual survival times. But now we'll create censoring. I'm going to randomly pick 30% of the individuals, and for each one of those, I'm going to subtract off some randomly generated small number to make it so that what we actually observe for those individuals is less than or equal to the true death time. And then delta is going to be 1 for everybody who's uncensored and 0 for everybody who is censored. Okay, and then to do a Kaplan-Meier survival curve estimate, we use this syntax. We use serve fit. Remember that to specify a survival response, we have to wrap it up in a capital serve wrapper. Capital serve takes event times and censoring indicators. So I'm saying fit a survival curve using this as the response, and tilde1 means I only have one comparison group. I don't need multiple survival curves. We'll change that in a minute and have 2 survival curves. So this gives us the survival curve estimate. And the picture. I don't want par anymore. Survival curve estimate from Kaplan-Meier with confidence bounds all the way down. Okay, now let's switch gears and think about a likelihood-based, a parametric estimate of survival. So let me go back to our notes. Likelihoods. Brief review. If we have just univariate data, no censoring, no correlation or anything, an IID sample, x1, x2 to xn, that is IID from some distribution with parameters theta. That could be normal with parameters mu and sigma squared. It could be anything though, as long as we specify what it is and we have specific parameters. Then the likelihood function, which is expressed as a function of the parameters, is just the product of the densities evaluated at each of our observed data points. That's what a likelihood is. And a maximum likelihood estimator, theta hat, the MLE, is the value of theta that maximizes the likelihood. So we're searching for choices of the parameters that make this likelihood, which is roughly speaking like a probability of seeing our data, which makes it biggest. Which parameter choices are most consistent with the data we saw? What's nice about maximum likelihood is that we know some good things about its characteristics. A MLE is approximately normal, for example, with mean equal to the truth, and a covariance matrix that we can calculate. I'm not going to write it down though. The good news is that when we do maximum likelihood, inference, confidence intervals, and hypothesis tests follow at least approximately by mathematical results like this one. So let's think about what a likelihood would look like with censored data. We have we're going to say T is the event time and delta is the censoring indicator. 0 if right censored, 1 if it's an actual death. And for convenience, we're going to define Y as log event time. So let Y be the log event time, and suppose that Y has some parametric distribution, F, that's parameterized by parameters theta. Could be normal, could be gamma, could be whatever, just some distribution that we specify. So suppose we have an uncensored observation. Log event time was observed to be Y sub I, and because it's uncensored, delta I is equal to 1. What should be the contribution to the likelihood for that type of individual? When we have IID data, each individual contributes to the likelihood by multiplying. So every individual contributes with a multiplicative factor. And everyone in this case is just the same density multiplied each time, but evaluated at each xi. It's a little bit different now with censored data. The likelihood contribution needs to involve both the event time and the censoring indicator. If we were to randomly draw from the population, it's like we observed an event time of such and such, and that event time was uncensored. So we really need to think about probability of getting this event time and that it was uncensored. The likelihood contribution is a joint probability. Probability that y is equal to little y and delta is equal to 1. And then with joint probabilities, if we recall basic probability theory, probability that x equals little x and y equals little y is equal to a conditional probability, y equals little y, given x equals little x, times a marginal probability. Just for any two random variables x and y. A joint probability can be written as a conditional times a marginal. In our case, we have yi equal to log ti, and we have the censoring indicator. So for this, the probability of observing little yi and an uncensored little yi is conditional times marginal. Probability that yi is little yi, given that it's an uncensored observation, times a marginal probability of an uncensored observation. And we're going to use notation to replace that marginal probability with something called pi1. So this turns into probability that y is little y, given that delta is equal to 1, times what we'll call pi1. That's what's in the notes. This joint probability of an event time and uncensored is equal to conditional probability of that event time, given that it's uncensored, times the probability that it was uncensored. And for uncensored individuals, the event times are just coming from this distribution. They are just realizations from this parametric distribution that we chose. So this can be simplified to just evaluate the density at little yi times the probability that it was an uncensored observation. For a censored observation, we don't know the exact event time. All we know for this individual who is censored is that their event time is bigger than or equal to the one we observed, and that it was a censored observation. So here again, we can say that's a joint probability. What's the probability of seeing an event time at least little yi and it being censored? And write that as a conditional, so let me write it over here. For a censored individual, we have the probability that y is at least little yi and censored, which is equal to joint times marginal, given censored times probability of censored. So if pi1 was defined as the probability of an uncensored observation, then 1 minus pi1 is the probability of a censored observation. So it looks like that. And then in terms of the parametric model, that f, f sub theta, that conditional probability, the probability of at least yi would be it'd be a right tail probability, right tail area under the curve probability of f theta, which is equivalent to 1 minus the CDF of theta evaluated at yi. Remember, the CDF is equal to a left tail probability. Capital F of y would be the probability that y is less than or equal to y. So if I want greater than or equal to y, I can do 1 minus the CDF. So we have n individuals. Each individual, we have an event time and a censoring indicator. For every individual that was uncensored, the likelihood contribution, forgot to write this part in, is the density times pi 1. For any individual who is censored, the likelihood contribution is 1 minus the CDF at yi times 1 minus pi 1. So now we can put that all together, and this is at the top is a likelihood for right-censored data. It's a product, just like all the likelihoods we have seen have been. And there's different contributions depending on whether it was an uncensored or a censored individual. Uncensored individuals will have delta equal to 1. So we have two pieces. We have something raised to delta, and we have something else raised to 1 minus delta. When delta is 1, the first piece turns on, and the second piece turns off. As in, the second piece becomes something raised to 0, or just 1. So for an uncensored observation, what that top expression looks like is just this. If the ith individual was uncensored, then its contribution to the likelihood is to multiply by this. And then the other way, for an uncensored observation, if an uncensored observation has delta equals 0, this first piece goes away because it's something raised to 0, and this piece shows up because it's something raised to 1 now. And that something that shows up is what we figured out on the whiteboard. It's a right tail probability times the probability of censoring. So the good news is we now have a likelihood. If we pick a distribution, does not have to be normal. It could be gamma, it could be Weibull, it could be lots of different things. Just pick a distribution f with parameters theta. This expression would hold as a likelihood for your right-censored data. And with the likelihood, we could estimate many things. We could estimate the survival probabilities. We could estimate the mean survival time. We could estimate the median survival time. Variances. We can do lots of things. It's usually easier when we're doing likelihood-based inference to work with a log likelihood rather than a likelihood itself. So the next expression is what happens if you log transform. The log of a product is the sum of the logs, and log of something raised to the power of delta is delta times the log of the something. So that's all that has happened here. And then the last line took everything that did not depend on theta and gathered it up into some arbitrary constant that we don't actually care about. If I'm doing likelihood-based inference, I want to maximize the likelihood with respect to theta. So anything that does not depend on theta, when I start differentiating with respect to theta, goes away. So as far as we care, it's a constant that does not depend on theta plus something that does depend on theta for the uncensored individuals plus something that depends on theta for the censored individuals. And if it were analytically tractable, we could just do calculus and differentiate this, set it equal to 0, solve for the values of theta that maximize it. I'm not going to have you do that. Instead, we're going to use an optimization algorithm in R to do the maximization. So what I'll show you in the script in just a second here is how we can do that maximum likelihood estimate when we have normally distributed log survival times. If we say f theta is normal with mean mu and variance sigma squared, then theta is the two parameters mu and sigma squared. And what we need to do is maximize the log likelihood with respect to those two things. Once you have that estimated, then the survival function is just estimated as a normal survival function, 1 minus the normal CDF, with estimated parameters that we got by maximizing the likelihood. What we're about to do over in the script is maximum likelihood to estimate mu and sigma squared for censored data, and then replace our rough step function estimate, the Kaplan-Meier estimate of the survival curve, with a smooth parametric curve. So let's go back here. And what I'm going to do is a couple of things. In your homework, you're going to do optimization using this function called Optum. Let's look at the help file for Optum real quick. So there are a couple of these types of functions in R. Optum does general purpose optimization, and it can work with vector valued parameters. So I can ask it to maximize a function with respect to mu and sigma squared. The way that we're going to call it is, say, Optum, first argument needs to be initial values. So this is an iterative algorithmic numerical method for maximization. It's not doing calculus. What we generally have to do with those types of algorithms is tell it where to start. What's a good initial choice for mu and sigma squared? We provide that. The second argument is a function that it can call repeatedly. So it needs to be a function of the parameters. It is the function we want to maximize. In our case, it needs to be a log likelihood. So we're going to need a function that codes up log likelihood for right censored data in terms of a normal distribution. We can specify a region over which to search if we want to prevent it from going off into infinity. These algorithms aren't guaranteed to give you the right answer. If you give it bad starting values, for example, it might get lost and never converge. So there are ways to kind of make it restrict its attention to a small subset of possibilities. All right. Before I show you the use of Optum, let me show you a more brute force approach that is arguably easier to understand. First thing I'm going to do, we have already simulated our survival data, right censored data. First thing I'm going to do now is code a function that will evaluate the log likelihood. You tell it theta, which equals mu and sigma, not sigma squared, but sigma. You tell me theta, this function will spit out the log likelihood. All this is in here, the objective function that's being returned, is what we have in the notes, excluding the constant, which is irrelevant to the process. So we have where I'm coding up a function that does sum of delta times log of the normal PDF evaluated at y, plus the sum of 1 minus delta times log of 1 minus the CDF of y. Sum of delta times log of the PDF, and we're assuming normality, so I'm using dnorm to evaluate the PDF at y with the current choice of mu and sigma, plus the sum of 1 minus delta times log of 1 minus the CDF. A CDF for a normal can be gotten with p norm. D norm, D binom, D poise, D gamma, those are all PDFs or PMFs. P norm, P binom, P beta, and all that, those are CDFs. And then what I'm going to do, this is not the recommended way in general, but this is like brute force style that all we're going to do is create a grid of mu values to consider and a grid of sigma values to consider. And we're going to go through every single combination of those choices and evaluate the log likelihood. I'm going to consider 500 possible values for mu between 3 and 7. I know what the true mu is because we're playing pretend. We simulated mu equal to 5. Obviously, you wouldn't know that in practice, but you could get a rough guess for what the mean is and go out plus or minus some reasonable distance. Sigma is actually 1.5. I'm going to consider values of sigma ranging from 0.75 up to 2.25, 500 different choices. Then I'm going to create an empty container, 500 by 500 matrix, and the ijth entry will be the log likelihood corresponding to the ith choice of mu, jth choice of sigma. And then what we would want to do is find where is the maximum. Out of that 500 by 500 matrix of log likelihood values, where's the biggest one? And whichever ij combo it is that has the biggest value, that's our maximum likelihood estimator. So I ran the code, and then I made a picture to visualize it. I used the contour function, which draws in 2 dimensions, or tries to draw in 2 dimensions, a 3-dimensional picture. So imagine you're looking down on a hill, and these contours show you areas of similar height. So inside the little oval in the middle, the ellipse in the middle, that's the peak. That's where the highest values are, and then it's tailing away as you move away from that. Can't see with great precision, but the MLE would be somewhere right in the middle of this ellipse at the top of the hill. That corresponds to about 1.6 or 7 for sigma and about 5.5 for mu. Those aren't exactly equal to the truth, but we're not guaranteed that an estimate will equal the truth. When we get a sample of data and we use a sample mean to estimate the mean, it's an unbiased estimate, but it won't equal the truth. On average, it will equal the truth. So this is not reflecting a problem, the fact that we don't have this thing centered right at the truth. If we simulated many, many times, on average, the MLE would be right at 5, and that for sigma would be right at 1.5. But for our specific observed sample of 100 observations, it looks like we have an MLE of about 5.5 for mu and about 1.6 or 7 for sigma. We can find where the maximum is. Let's see if I can figure out how to do that. I think there's a function that will make it really easy to find which exact location corresponds to the maximum. Yeah, I think I can use the which function. If I say which and some criterion, go find the place where objective grid equals the maximum of objective grid. And if I say array.index equal true, it will give me back the row and column number that contain the biggest value. So I should be able to go to objective grid, row 302, column 281, and that's our maximum, that's our maximized likelihood. That means that the MLE of mu is the 302nd element of mu grid. And our MLE of sigma is the 281st element of the sigma grid. We have an MLE of mu hat equal 5.4, sigma hat equal 1.6. So that's one kind of generic way to optimize things. If you don't know how to use an optimization function, you can always do rough kind of exhaustive search, grid searching. It's not efficient at all when it comes to real-world data sets. You can do a lot faster if you use, say, Optum in R or something like that in another software. So now let's use Optum and see what it gives us. It should give us basically the same answer. Optum, let me go back to the help file one more time. What Optum is going to do is maximize. It is going to optimize or maximize. No, I'm sorry. Here we go. By default, Optum minimizes. Sorry. Optum, by default, minimizes. You can force it to maximize, but I'm going to force it to maximize just by changing the function that I give it. If Optum wants to minimize, but I want a maximum likelihood, I want to maximize the likelihood, all I need to do is give it, instead of the log likelihood, the negative log likelihood. If you minimize the negative log likelihood, it's equivalent to maximizing the log likelihood. So here is neg log like, which is just evaluate the log likelihood and return the negative of that. To use Optum, there's two arguments again. The first one is starting values. Tell the algorithm your best guess at the values of theta to get it started, and then it will use clever math and computer science to iterate until it maximizes. So the second function is the function that we want to optimize. Reasonable starting values with survival data. How would you estimate the mean survival time? Well, one way you could do it is just ignore the censoring and compute the average of just the event times. Same thing for the standard deviation. One thing we could do just as a rough guess is compute the standard deviation, ignoring the survival times. Probably a better choice would be compute the mean of the response of the survival times among those who were not censored, and the standard deviation among those who were not censored. I don't think it makes a difference in this particular example. So let's try it. What do we get back? Notice that that took virtually no time at all, whereas the group or the loop that I had up above took a few seconds. All right, so according to Optum, the maximized log likelihood is minus 145.1344. We computed with our grid search almost the same thing. And then the maximum likelihood estimators are almost exactly the same as ours as well. Ours are necessarily going to be coarser than this algorithm will find, because we just created like a partition of possibilities. Whereas this function can consider any real valued possibility. It took it 49 iterations. It had to call our function, our log likelihood function, 49 times. It gives us a code in the convergence element that, if you look at the help file, that tells you did it converge or not, in addition to some other things. So be aware whenever you use some kind of algorithm, numerical algorithm like this, there's no guarantee that it worked. You want to look at some summary of its performance to indicate did it converge or not. If it didn't converge, then don't trust the results. Convergence equals 0 is indicative of no problems, if you look at the help file. Okay, we are out of time. What's next is comparing. Well, let's go ahead and make this picture. Now that we have survival MLEs, we can add to our picture of survival curve a parametric estimate of the survival function. So the red curve is a normal-based survival curve, 1 minus the CDF, where we've plugged in our MLE estimates of mu and sigma. And it tracks the Kaplan-Meier curve pretty closely. It's nicer, arguably, because it's smooth like that. Okay. Next time, I'll show you how to compute mean survival time from a Kaplan-Meier curve and from an MLE-based curve, how to compute median survival time. Then we'll look at the two-class case like your homework, like number 1 in your homework, and see how to use the log rank test to put a p-value on, is the survival prognosis in this group the same as that group. Okay? Have a good weekend.